Picture for just a moment the universe in its infancy, a vast, silent darkness stretching endlessly in every direction, a canvas waiting for the first brushstrokes of light to appear. What secrets lie hidden in those first moments, that mysterious period scientists call the Cosmic Dawn era? It's a time so ancient that it predates even the birth of the very first stars and galaxies, a chapter of cosmic history written in darkness and silence, yet holding the keys to everything we see around us today. This era, stretching from the aftermath of the Big Bang to the dawn of structure in the cosmos, is more than just a scientific curiosity. It's a frontier of human understanding, a realm of profound unknowns that challenge our deepest assumptions about existence itself. We're about to embark on a journey through this extraordinary epoch, a voyage into the very origins of reality as we know it, from the cosmic microwave background, the faint afterglow of creation, to the formation of the very first luminous objects. The Cosmic Dawn era is filled with puzzles that have intrigued astronomers, philosophers, and dreamers for generations. It's a story written in the language of physics, but one that touches on something universal: our innate desire to understand where we came from and how this breathtaking universe began to take shape. And as we peel back the layers of time, we'll uncover not just scientific facts, but moments of sheer wonder that connect us to the cosmos in ways we're only beginning to grasp. Together, we'll explore 25 of the most fascinating mysteries tucked within this formative era. Questions about dark matter's role, the nature of the first stars, and how emptiness gave way to complexity. Each mystery is a piece of a grand puzzle, one that scientists around the world are racing to solve using cutting-edge telescopes, simulations, and sheer human ingenuity. This isn't just a story about the past, it's about our future and our place in a cosmos that is still revealing its secrets. So settle in, open your mind to the possibilities, and let's journey back to the very dawn of everything. Our journey into the cosmic dawn begins with the very first architects of light, a generation of stars so strange and magnificent that they defy our everyday experience. These are population 3 stars, the universe's pioneering luminaries, and their nature remains one of the most compelling puzzles in all of cosmology. Unlike our own sun, which is enriched with elements like carbon, oxygen, and iron, these primordial giants were forged from a pristine soup of only hydrogen and helium, the raw elements left over from the Big Bang itself. This pure composition meant their internal physics operated under entirely different rules, leading them to grow to almost unimaginable scales. We're talking about behemoths that could have been hundreds, even 1,000 times more massive than our sun, burning at ferocious temperatures and living short, spectacularly violent lives. Their brilliance was likely a deep blue or even ultraviolet, flooding the nascent cosmos with its first true light and beginning the crucial process of reionization, which ultimately cleared the cosmic fog that had blanketed the universe. The reason we've never directly seen one of these stellar titans is simply a matter of time and distance. Their light has been traveling toward us for over 13 billion years, stretching with the expansion of the universe into the far infrared part of the spectrum, a range incredibly difficult to observe from within our atmosphere. Furthermore, their entire lifespan was a cosmic blink. They lived fast and died young in just a few million years, but we are not entirely without clues. Their existence is written into the very fabric of the universe they helped create. The cataclysmic deaths of these first stars as supernova of such staggering power that they dwarf anything in the modern universe were the cosmic forges that created the first heavy elements. In their fiery final moments, they fused hydrogen and helium into the first traces of carbon, oxygen, silicon, and iron, then scattered these precious ashes across the cosmos. This act of stellar alchemy was the crucial first step in moving the universe from a simple state of pure hydrogen and helium to a more complex one, rich with the diversity of elements that would eventually form rocky planets, oceans, and life itself. They are the silent, unseen ancestors to every star that followed, including our own sun, and to every element that makes up our world and our very bodies. Yet as profound as their impact was, that first light from population 3 stars had to fight its way through a universe still shrouded in a primordial fog. This brings us directly to our second profound mystery, the great cosmic dawn event known as reionization. Think of the early universe not as the crystal-clear void we see in telescope images today, but as a realm filled with a dense, neutral hydrogen gas. This gas acted like a pervasive cosmic fog, absorbing the energetic ultraviolet light from those first stars and galaxies, preventing it from traveling very far. For the universe to become transparent, for that light to finally travel freely across billions of light years and into the lenses of our telescopes, that fog had to be lifted. This process is what astronomers call reionization, and it represents one of the most significant phase changes in the entire history of the cosmos, the moment the universe switched on the lights for good. The central puzzle isn't whether reionization happened. We know it did because we can see the clear universe around us. The mystery lies in its timeline. When exactly did this epoch begin? How long did it last? And what were the primary sources of the ionizing radiation that made it happen? Was it driven predominantly by the fierce radiation from those massive population 3 stars, or by the collective output of early galaxies filled with more modest stars? Or perhaps even by more exotic objects like quasars fueled by voracious black holes? This is not just a question of dates on a cosmic calendar. Pinpointing the timeline of reionization is absolutely crucial because it acts as a direct record of how and when the first structures of the universe gained enough influence to permanently alter their entire environment. It marks the end of the cosmic dark ages and the beginning of the universe as we recognize it. The challenge in solving this mystery comes from conflicting evidence gathered by our most powerful observatories. Data from the Planck satellite, which studied the cosmic microwave background, suggests reionization was a relatively late and rapid process, concluding around when the universe was roughly 550 million years old. The subtle imprint left by free electrons on the microwave background points toward this timeline. However, observations from the Hubble Space Telescope present a different story. By peering at some of the most distant galaxies ever seen, galaxies that existed when the universe was only 400 million years old, Hubble found evidence that these early objects were already surrounded by clear, transparent space. This implies that the process of reionization was already well underway and perhaps even nearing completion much earlier than Planck's data suggests. This discrepancy leaves cosmologists with a fascinating problem. It's as if 2 different historical records of the same event disagree on the fundamental sequence of what happened. Resolving this conflict is a primary driving goal for the James Webb Space Telescope. With its unprecedented infrared vision, Webb is designed to look directly back into this era, to census the population of early galaxies and measure their ionizing power. By finally getting a clear view of the actors on the stage during the cosmic dawn, Webb could determine if there were enough early stars and galaxies to lift the fog so quickly, or if our understanding of the sources of reionization is somehow incomplete. Unlocking the timeline of this great transformation is like finding the missing chapter that explains how a universe of darkness became a universe of light, a fundamental step in the journey that led to us. This leads us directly to a third great puzzle of the cosmic dawn, the identity of the universe's very first light bulbs. We know the fog was lifted, but what precisely flipped the switch? Was it the searing ultraviolet radiation from those colossal first stars? Or was it the even more intense glare from the voracious supermassive black holes known as quasars, gobbling down matter at the hearts of the earliest galaxies? Or perhaps something even more exotic and unexpected. This isn't just an academic debate. It's a fundamental question about the primary drivers of change in the infant universe, and the answer shapes our entire understanding of cosmic evolution. The case for massive stars is a compelling one. As we've seen, population 3 stars were titanic factories of ionizing photons. Their sheer power and numbers spread across the early cosmos could have provided a widespread and steady source of the energy needed to strip electrons from hydrogen atoms. Imagine a vast, dark countryside slowly being illuminated by the kindling of countless campfires, each one a young galaxy blazing with brilliant new stars. This stellar first model paints a picture of a universe gradually awakened by the collective effort of its first stellar inhabitants, a bottom-up process where small structures collectively change the entire cosmos. On the other side of the argument, quasars present a very different, more dramatic scenario. A quasar is powered by a supermassive black hole, millions or even billions of times the mass of our Sun, as it consumes vast quantities of gas and dust. The incredible friction and gravity in the swirling disk of material around the black hole heats it to unimaginable temperatures, causing it to glow with a brilliance that can outshine an entire galaxy. A single quasar can flood its entire region of space with a flood of high-energy radiation, potentially reionizing vast bubbles of the cosmic fog far more efficiently than a comparable region of stars. This black hole first model suggests the dawn was broken not by a chorus of countless stars, but by the occasional blinding lighthouse beam of a quasar, punching through the darkness and clearing the fog in massive, isolated pockets. Distinguishing between these two scenarios is one of the toughest observational challenges in modern cosmology. The light from this epoch is incredibly faint and has been stretched into the far infrared by the expansion of the universe. Furthermore, the era we're trying to study is also the very same era that was shrouded in the neutralizing hydrogen fog, making direct observation exceptionally difficult. Scientists therefore have to be detectives, looking for indirect clues left behind in the light we can see. One major line of evidence comes from the cosmic microwave background. The Planck satellite's detailed maps of this afterglow contain a subtle imprint of how the free electrons produced during reionization scattered the microwave light. This imprint can tell us about the timing and duration of reionization. A process driven by stars which form in many places at once would likely have been more gradual and uniform. A process driven by rare, incredibly bright quasars might have been more patchy and rapid, creating a different statistical signature in the microwave background. While data leans towards a more gradual process, the evidence isn't yet conclusive enough to rule out either contributor. The other approach is to use powerful telescopes like Hubble, and especially the James Webb Space Telescope, to try and directly census the population of early objects. By counting the number of early galaxies and estimating their stellar populations, astronomers can calculate how much ionizing radiation they collectively produced. Similarly, by searching for signs of early quasars, they can gauge their abundance and power. The initial results from Webb are already deepening the mystery. It has found more small, faint galaxies in the early universe than many models predicted. This suggests stars may have been more numerous and influential than we thought. Yet, it has also discovered evidence of surprisingly large black holes existing very early on, suggesting they, too, could have played a significant role. The most likely answer is that it wasn't a simple either-or scenario, but a complex cosmic collaboration where both stars and black holes contributed to lighting up the cosmos. Determining their exact share of the work, however, remains an open and intensely investigated mystery. This brings us to one of the most head-scratching enigmas of the early cosmos, the astonishingly rapid appearance of supermassive black holes. The sheer speed of their formation defies our conventional understanding of how these gravitational monsters grow. We find evidence of behemoths weighing 1 billion times the mass of our Sun, already fully formed, in a universe that was less than 1 billion years old. To put that into perspective, that's like finding a fully grown ancient redwood tree in a forest that was only just planted a few weeks ago. The process of building a black hole of that size should take an incredibly long time, as it slowly consumes gas and dust from its surroundings. But the cosmic clock from the Big Bang to these mature giants simply didn't have enough ticks for such a leisurely meal. So how did they get so big so fast? This puzzle forces us to reconsider the very mechanisms of black hole birth and growth in the universe's first moments. Scientists are actively investigating two primary, competing theories for this rapid formation, each with its own compelling evidence and significant challenges. The first and more traditional idea is known as the stellar seed model. In this scenario, the very first generation of stars, those colossal population, 3 stars we discussed, lived their short, violent lives and then collapsed under their own immense gravity. When a star that massive dies, it doesn't just go supernova. It can potentially collapse directly into a black hole, creating a primordial seed with a mass maybe 100 times that of our Sun. This seed then settles into the dense core of a young galaxy and begins its slow but steady diet, feeding on the abundant gas around it. Through mergers with other black holes and periods of intense accretion, it could, in theory, grow to supermassive proportions over hundreds of millions of years. The problem with this stellar seed theory is the intense pressure of time. Even with a voracious appetite, a black hole faces fundamental physical limits to its growth rate, known as the Eddington limit. This is the maximum rate at which a black hole can consume matter before the intense radiation pouring out from its accretion disk actually pushes away the very gas it's trying to eat. It's like trying to drink from a fire hose. The force of the water makes it impossible to take a big gulp. To reach 1 billion solar masses so quickly, these early black holes would have needed to consistently feed at super Eddington rates or find some way to bypass this limit entirely, which is a major point of investigation. This difficulty has led some cosmologists to propose a far more dramatic and exotic alternative, the direct collapse model. This theory suggests that under just the right conditions, immense clouds of primordial gas in the early universe could have collapsed directly into a massive black hole seed, skipping the star-forming stage altogether. Imagine a vast, heavy cloud of pure hydrogen and helium swirling in the darkness, without heavier elements to help it cool and fragment into many smaller stars. This entire gigantic cloud, weighing tens of thousands or even hundreds of thousands of solar masses, could catastrophically collapse in on itself in a single, swift event. The result wouldn't be a star, but a massive black hole seed born already middle-aged, giving it a huge head start on the path to becoming a supermassive giant. This would solve the timing problem neatly, but it requires very specific, pristine conditions that may have been rare in the early cosmos. The implications of solving this mystery stretch far beyond just understanding these exotic objects themselves. It is fundamentally intertwined with the story of how galaxies, including our own Milky Way, came to be. Nearly every large galaxy we observe has a supermassive black hole at its center, and there appears to be a fascinating and mysterious correlation between the mass of the central black hole and the properties of the galaxy's surrounding bulge of stars. This suggests that the formation and growth of a galaxy and its central black hole are deeply connected, a cosmic dance of gravity and feedback. Did the black hole form first and help shape the galaxy growing around it? Or did the galaxy form first, funneling gas to the center to feed the nascent black hole? The answer to how the first black holes formed so quickly is a critical key to unlocking this chicken and egg problem of cosmic evolution. But to truly grasp how these first structures, whether stars, galaxies, or black holes, could form at all, we must turn our attention to the invisible architect of the cosmos, dark matter. This mysterious substance, which does not emit, absorb, or reflect light, is the hidden framework upon which the entire visible universe is built. Its gravitational pull is the cosmic glue that holds galaxies together and dictates the large-scale structure of everything we see. And its role was absolutely paramount during the cosmic dawn, acting as the essential scaffolding that guided the formation of the very first luminous objects from the formless primordial darkness. In the immediate aftermath of the Big Bang, the universe was an incredibly smooth, nearly uniform soup of particles, but it wasn't perfectly smooth. Tiny, random quantum fluctuations imprinted minuscule variations in density. Some regions were ever so slightly denser than others. And because dark matter makes up the vast majority of matter in the universe, it was these dark matter density fluctuations that truly mattered. Dark matter, being unaffected by the intense radiation pressure that buffeted normal matter, was free to begin collapsing under its own gravity far earlier than atoms could. Think of it like this: in the early universe, normal matter, the protons and electrons that make up gas, was like a light foam being tossed on the waves of radiation, unable to clump together. Dark matter, however, was like a heavy anchor sinking silently to the bottom, unaffected by the storm above. It began to form a vast, invisible network of filaments and halos, a cosmic web of gravitational potential wells. It was into these pre-existing gravitational pits carved out by dark matter that normal matter eventually flowed. As the universe expanded and cooled, the radiation pressure lessened, allowing atoms of hydrogen and helium to finally feel the gravitational tug of the dark matter structures and fall into them. This is why the properties of dark matter are literally written into the distribution of the first galaxies. The specific way dark matter clumps together, how it forms halos of different sizes, and how those halos are distributed across space directly determined where the first stars would ignite and the first galaxies would assemble. If dark matter had different properties, if it were warmer or moved faster, for instance, the entire blueprint for cosmic structure would be different. The pattern of galaxies we see today is a fossil record of dark matter's inherent nature. This is why astronomers are on a dedicated hunt to find the very faintest, most ancient galaxies. By mapping the distribution of these pioneer galaxies from the cosmic dawn, we are effectively creating a three-dimensional map of the dark matter scaffolding at that time. Powerful observatories like the James Webb Space Telescope are peering back to these epochs not just to see the galaxies themselves, but to use them as tracers to illuminate the invisible dark matter structures they are embedded within. Every faint red smudge of a primordial galaxy discovered by Webb is like a single light bulb switched on in a vast, dark cathedral, slowly revealing the hidden arches and buttresses that hold the entire edifice up. By studying the precise clustering of these early galaxies, how they are grouped and spaced, scientists can work backwards to infer the properties of the dark matter that dictated that pattern. This incredible detective work is our best hope for answering some of the most fundamental questions about dark matter itself. Is it cold, meaning its particles move relatively slowly, allowing it to clump efficiently into small-scale structures first? This is the prevailing model, and it predicts that the earliest universe should be filled with a plethora of tiny dark matter halos, which would then host a multitude of small, faint galaxies. Or is it warm, with particles moving at a significant fraction of the speed of light, which would suppress the formation of very small structures? A warm dark matter universe would have far fewer tiny primordial galaxies. The census of ultra-faint galaxies from the cosmic dawn being conducted by Webb is therefore a direct test of these theories. The initial abundance of small galaxies it is finding seems to support the cold dark matter model, but the investigation is ongoing, and each new observation sharpens our understanding of this invisible cosmic architect. Without dark matter's gravitational blueprint, the universe might have remained a forever dark and formless void. Decoding its role is key to understanding our very origins. Yet for all its apparent success, this elegant model of cosmic construction faces a startling and significant challenge when we compare its predictions to what we actually see in the sky around us. The most sophisticated supercomputer simulations of the universe, which meticulously follow the rules of gravity and the expected behavior of dark matter, paint a very specific picture of a young galaxy like our own Milky Way. They show it should be surrounded by a vast, bustling swarm of thousands of smaller satellite galaxies, cosmic minnows, swimming in the gravitational wake of a much larger whale. These are the dwarf galaxies, the fossil remnants of the first small structures to form in the universe, and according to the simulations, they should be everywhere. But when astronomers go looking for them with our most powerful telescopes, they find only a tiny fraction of that predicted number. This glaring mismatch between theory and observation is known as the missing dwarf galaxy problem, and it represents a serious crack in the foundation of our understanding of galaxy formation. Think of it as a cosmic census that came up wildly short. Our local galactic neighborhood, the region gravitationally bound to the Milky Way and our sister galaxy Andromeda, should be teeming with hundreds of these small, faint galaxies. Yet to date, we've only confidently identified about 60. It's as if we predicted a massive metropolis based on all the known rules of urban development, but when we arrived, we found only a small village. This isn't just a minor accounting error. It's a fundamental discrepancy that forces us to question whether our models are missing a crucial piece of physics, or if our understanding of dark matter itself is somehow incomplete. Scientists have proposed several compelling solutions to this puzzle, each exploring a different facet of cosmic physics. One prominent idea focuses on the incredible power of feedback from those first generations of stars. The earliest stars were not gentle neighbors, they were colossal, volatile, and short-lived. When they died in spectacular supernova, they didn't just forge new elements, they unleashed unimaginable torrents of energy and powerful winds of gas. This furious feedback could have physically blasted the raw star-forming gas right out of the smallest, most vulnerable dark matter halos. Without this essential fuel, these potential dwarf galaxies would have been stillborn, their growth stunted before they could ever truly ignite and become visible. In this scenario, the dwarfs aren't truly missing. They failed to form in the first place because the early universe was too violent and chaotic a nursery for the most delicate structures to survive. Another fascinating possibility delves into the very nature of dark matter. The standard model of cosmology uses what's called cold dark matter, where the particles move relatively slowly. This allows it to clump efficiently, forming that plethora of small-scale structures. But what if dark matter is slightly different? Theories involving warm dark matter propose particles that move at a significant fraction of the speed of light. This extra motion would create a sort of gravitational pressure that prevents dark matter from clumping on the smallest scales. It would effectively erase the tiniest dark matter halos from the cosmic blueprint from the very beginning. If warm dark matter is real, the simulations were wrong to predict so many small halos in the first place, neatly explaining why we don't see the galaxies that would have formed within them. The dwarfs are missing because the gravitational pits they were meant to form in never existed. A third, and perhaps more humbling, explanation lies not in the laws of physics but in the limitations of our own technology. The predicted missing dwarfs are not giant, bright spiral galaxies. They are expected to be incredibly faint, diffuse, and composed mostly of dark matter with very few stars. They could be lurking in the darkness right under our noses, but because they contain so few luminous stars, they are phenomenally difficult to detect. Modern sky surveys are constantly pushing the limits of sensitivity, and with every improvement, we do indeed discover new, ever fainter dwarf galaxies. The revolutionary Vera C. Rubin Observatory, set to begin operations soon, is specifically designed to conduct an unprecedented deep survey of the sky. It may finally reveal this hidden population of ultra-faint dwarfs, showing that they were there all along, just waiting for a powerful enough eye to find them. Solving this mystery is about more than just completing a cosmic head count. It's a critical test for the entire standard model of cosmology and a direct window into the powerful forces that shaped the universe's first structures. But while dark matter provided the invisible gravitational blueprint for cosmic structure, there is another, far more subtle force woven through the fabric of the universe, one whose origins are even more enigmatic: magnetism. We are so accustomed to magnetic fields in our daily lives, from the humble refrigerator magnet to the compass that points north, that it's easy to forget their presence on the cosmic scale is a profound mystery. Vast, invisible magnetic fields permeate the space between galaxies, threading through galaxy clusters and stretching across the cosmic web itself. These fields are incredibly weak, millions of times weaker than Earth's own magnetic field, but their sheer scale is mind-boggling, influencing the motion of cosmic gas, guiding high-energy particles, and shaping the birth of stars. The central question, known as Mystery 7, is a classic cosmic chicken and egg problem. Where did these immense magnetic fields come from? Were they somehow imprinted into the fabric of reality in the first moments after the Big Bang, a primordial seed present at the very beginning? Or were they painstakingly built from nothing later on, generated and amplified by the dynamo action of the first stars and galaxies? The idea of a primordial origin is captivating. It suggests that the initial conditions of the universe included not just matter and energy, but also fundamental magnetic fields, perhaps generated during a phase transition in the extremely early cosmos, like the inflationary epoch. In this scenario, the entire universe was born magnetized, with these weak fields already stretched across the nascent cosmos, simply waiting for the formation of large-scale structures to give them a canvas upon which to play. This would be an elegant solution, providing a ready-made explanation for why we see magnetism everywhere we look. However, there is a significant hurdle for this theory. The violent, hot plasma of the early universe was an excellent conductor of electricity. Any primordial magnetic fields present would have been effectively frozen into this searing soup, their strength and structure locked in place. As the universe expanded, these fields would have been diluted, stretched, and weakened by the incredible growth of space itself. The fields we observe today, as faint as they are, might actually be too strong to be easily explained by this simple dilution of a primordial seed. This has led many scientists to lean toward the alternative, a bottom-up origin. This second theory posits that the first magnetic fields were not cosmic in scale, but incredibly local and tiny. They could have been generated in the turbulent aftermath of the first supernova, or in the violent shocks and shearing motions within the accretion disks around the first supermassive black holes. These processes could have created minuscule, microscopic magnetic fields, little more than a random magnetic whisper. The true magic, the part that turns a whisper into a cosmic hum, is the astrophysical dynamo. A dynamo works by taking a small, pre-existing magnetic field and amplifying it through the ordered, rotational motion of a conducting fluid like ionized gas. Imagine stirring a cup of coffee with a tiny magnet at the bottom. Your motion would slowly amplify the magnetic field. On a galactic scale, the differential rotation of an entire galaxy, where the inner parts rotate faster than the outer parts, acts as a massive, natural stirring mechanism. Over hundreds of millions of years, this slow, cosmic churning can take a weak, disorganized field and stretch, twist, and fold it, amplifying its strength exponentially until it becomes the large-scale, coherent field we can observe today. So how do we possibly distinguish between these two competing origin stories? The key lies in finding a fossil record, a way to peer back to the cosmic dawn and directly detect the magnetic fields that existed before galactic dynamos had much time to operate. This is where the study of light itself becomes our most powerful tool. When light travels through a magnetized medium, its electromagnetic waves can become preferentially aligned or polarized. It's a subtle effect, but it imprints a specific signature on the light, a kind of hidden code that astronomers can decipher. By analyzing the polarization of the very ancient light we receive from this era, particularly the faint, redshifted radio waves from neutral hydrogen, or the subtle polarization in the cosmic microwave background, scientists hope to find the fingerprints of these infant magnetic fields. The strength and structure of the magnetic fields detected at these extreme distances would be a dead giveaway to their origin. If we were to find evidence of surprisingly strong, well-ordered magnetic fields permeating the universe when it was only a few 100 million years old, it would be a massive boost for the primordial theory. It would suggest these fields were already established on large scales before galaxies had enough time to create them themselves. Conversely, if the fields from that time appear weak, patchy, and disorganized, it would strongly support the idea that they were only just being born in the hearts of the first stellar explosions, and that the great cosmic dynamos had only just begun their slow, patient work of amplification. Unlocking this mystery does more than just satisfy our curiosity about a fundamental force. It reveals another layer of the universe's complex history, showing us how even the most subtle energies can, over billions of years, come to shape the cosmos we call home. If you want to map the invisible structure of the early universe, you need a brilliant, distant lighthouse to act as your probe. For astronomers, these lighthouses are quasars, the intensely luminous cores of active galaxies powered by ravenous supermassive black holes. When we aim our most powerful telescopes at one of these cosmic beacons, we're not just collecting its light, we're intercepting a message that has traveled for billions of years, a message that has been subtly encoded by every cloud of hydrogen gas it passed through on its immense journey to Earth. The result is one of the most extraordinary and information-rich sites in all of astronomy, the Lyman Alpha Forest. The name itself is wonderfully evocative, and it perfectly captures what we see. When we break the quasar's light into a spectrum, spreading it out like a rainbow to reveal its constituent colors, we don't see a clean, continuous band. Instead, we find a veritable forest of hundreds, sometimes thousands, of sharp, dark absorption LINES Chinese letter Chinese letter Chinese letter Chinese letter ING the spectrum. Each one of these lines is like a cosmic receipt, a tiny bite taken out of the quasar's light by a specific cloud of neutral hydrogen gas at a specific point along the line of sight. Because the universe is expanding, each cloud is moving away from us at a different speed. This motion stretches the light, shifting the characteristic fingerprint of hydrogen absorption to a different, unique location in the spectrum. This allows astronomers to not only identify the presence of each cloud, but also to calculate its precise distance from us. The final spectrum is a staggeringly complex barcode, a vertical timeline of hydrogen stretching from the quasar all the way back to our telescope. This forest is so much more than a pretty pattern. It is a direct fossil record of the distribution of matter during and after the epoch of reionization. It shows us the cosmic web in a way that nothing else can. The dense trunks of the forest, the thicker, darker absorption lines, represent the denser filaments and knots of the web, the protogalactic regions where matter was collapsing to form the first structures. The thinner, more sparsely spaced lines represent the diffuse gas in the vast cosmic voids. By statistically analyzing the thickness and spacing of these lines, cosmologists can effectively perform a census of the universe's structure at different eras, building a three-dimensional map of how matter was clustered from the largest scales down to the smallest. However, interpreting this magnificent cosmic barcode is notoriously difficult, a puzzle wrapped in an enigma. The primary challenge is that a single line of sight gives us a one-dimensional slice through the universe. Imagine trying to understand the entire structure of a forest, the location of every tree, the shape of every hill and valley, by only looking at a single, incredibly long, straight path through it. You'd get an immense amount of detail along that line, but reconstructing the full three-dimensional topography from that single thread of information is a monumental task of statistical inference and complex computer modeling. The second and perhaps greater challenge is evolution. The light from a distant quasar has passed through hydrogen clouds from many different epochs. The clouds closest to us are relatively modern, while those near the quasar are from a much earlier time. The properties of the gas, its temperature, density, and ionization state, change dramatically over these cosmic timescales. A key goal is to find the so-called edge of the forest. As we look farther back, closer to the time of reionization, we expect to see a dramatic change. The number of neutral hydrogen clouds should increase enormously, eventually merging into a solid, continuous block of absorption known as the Gunn-Peterson trough. This trough is the spectroscopic signature of a universe still filled with neutral fog before the lights were switched on for good. Finding this transition point in the forest is a holy grail, as it would pin down the exact timeline of reionization. Yet, even this is not straightforward, as the process was likely patchy and uneven, creating a blurred edge rather than a sharp one. Despite these immense challenges, the Lyman Alpha Forest remains our most powerful tool for studying the intergalactic medium. It reveals the temperature and density of the primordial gas, provides clues about the intensity of the ultraviolet background radiation that ionized it, and even offers a way to measure the fundamental constants of the universe to see if they have changed over billions of years. It is a testament to human ingenuity that we can take the faint, ancient light of a dying quasar and from it, extract the blueprint of the cosmic web itself, reading the story of creation written in the shadows. And just as we grapple with the invisible forces and ancient light that shaped the cosmos, a new and startling mystery has burst onto the scene, one delivered by our most powerful window into the past. The James Webb Space Telescope was designed to see the first galaxies, but it appears to have found something that, according to our established theories, simply shouldn't be there. We expected to see infant galaxies, small, fragile, and primitive, the cosmic equivalents of toddlers taking their first unsteady steps. Instead, Webb has revealed celestial giants, galaxies that are astonishingly massive, incredibly bright, and surprisingly mature, existing at a time when the universe was only a few 100 million years old. This is like finding a fully grown adult in a nursery filled with newborns. It completely upends our understanding of how quickly structure can emerge from the primordial darkness. The sheer scale of these objects is what defies belief. These aren't just slightly brighter than predicted. Some appear to contain the mass of tens or even hundreds of billions of stars, rivaling our own Milky Way, but at a fraction of its age. Our standard models of galaxy formation are built on a foundation of cold, dark matter and hierarchical growth, where small structures merge over billions of years to build larger ones. There simply hasn't been enough time in the early universe for gravity to gather such an immense amount of material and then for stars to form so efficiently. The presence of these behemoths suggests that either matter clumped together far more efficiently than we thought possible, or that the very first stars formed at a rate that borders on the miraculous, converting nearly all available gas into stars in a frantic, explosive burst of creation. This unexpected brightness forces astronomers to consider a range of exotic explanations, each more fascinating than the last. One compelling possibility is that our assumptions about the stars inside these galaxies are wrong. Perhaps the initial mass function, the rulebook that dictates how many big versus small stars are born, was drastically different in the early universe. Instead of a normal distribution with many small, faint stars and a few giants, maybe these pioneer galaxies were dominated by an overwhelming population of brilliant, massive stars, making them inherently far more luminous per unit of mass than modern galaxies. This would mean they shine far brighter without necessarily requiring more total material, offering a way to explain the light without breaking the laws of physics. Another, more dramatic theory points to the potential role of supermassive black holes. What if the incredible light we're seeing isn't primarily from stars at all, but from the blazing accretion disks of hyperactive black holes at the center of these young galaxies? A single quasar can outshine its entire host galaxy, and if these black holes were already massive and feeding at a ferocious rate, they could be responsible for the overwhelming brightness Webb observes. This would neatly tie this mystery back to the puzzle of how supermassive black holes formed so quickly, suggesting that these two enigmas are deeply intertwined. Or the answer could lie in the very nature of star formation itself, maybe in the pristine environment of the early universe devoid of dust and heavy elements. The process of turning gas into stars was radically more efficient. Without the complex chemistry that later helped cool gas clouds and allowed them to fragment into many smaller stars, the first star-forming clouds might have collapsed monolithically, creating stars in a single, concentrated, and incredibly productive event. This would represent a mode of galaxy assembly we have never witnessed in the modern cosmos, a lost chapter of cosmic history where the rules were written differently. Each of these explanations carries profound implications. If it's the stars, we have to rewrite our models of stellar evolution for the earliest times. If it's the black holes, we must understand how they grew to such influence so rapidly. And if it's ultra-efficient star formation, we are seeing a unique, transient phase of the universe that was over almost as soon as it began. The James Webb Space Telescope is now engaged in a deep forensic investigation of these enigmatic objects, using its powerful spectrographs to dissect their light. By analyzing the specific signatures in their spectra, astronomers hope to distinguish between light from a frenzy of star formation and the fierce glare of an accreting black hole. The answer will not only solve this specific mystery, but will force us to refine, or perhaps even fundamentally alter, our core understanding of how the cosmos built its first and greatest structures. Yet for all the grandeur of galaxies and the violence of black holes, one of the most profound transformations of the cosmic dawn was happening on a scale infinitely smaller, in the quiet spaces between the first stars. This is the story of cosmic chemistry, the moment the universe learned to bond. After the Big Bang, the cosmos was a monotonous place, elementally speaking. For millions of years, it contained only three things: hydrogen atoms, helium atoms, and a sea of radiation. There were no planets, no rocks, no water, and certainly no molecules for life, because there were simply no other elements available to create them. The universe was a vast, elemental desert, but within that desert, the first miraculous bond was about to form, a partnership that would kickstart the chemical evolution of everything to come. This primal molecule is known as helium hydride, a simple union of a helium atom and a hydrogen ion, and its formation marks the true beginning of chemistry in the universe. The hunt for this molecule became a century-long scientific quest. Theoretically, we knew it had to be the first. In the cooling aftermath of the Big Bang, the universe was still too hot for neutral atoms to even exist. It was a searing plasma of naked atomic nuclei and free electrons. But as expansion cooled the cosmos, electrons were finally captured, forming the first stable hydrogen and helium atoms. However, in this new neutral universe, there was a problem. The first step in forming a molecule is for two atoms to meet and stick together, but hydrogen and helium are both noble gases, incredibly stable and content on their own. They are the introverts of the periodic table, reluctant to interact. How could a bond possibly form? The answer lay in a tiny, rare exception. In the vast sea of neutral gas, a few hydrogen atoms would occasionally be struck by the leftover radiation from the Big Bang, knocking off their electron and turning them into a positively charged hydrogen ion. This ion, hungry to regain its electron, is highly reactive. It could then attract and bond with one of the stable, neutral helium atoms, creating helium hydride ion, or He+. This was the very first molecular bond, a fragile foothold for complexity in a simple world. For decades, astronomers searched for the telltale signature of this molecule in modern nebulae, the remnants of dying stars, but found nothing. It seemed frustratingly elusive. The breakthrough finally came in 2019 with the sophisticated airborne telescope known as SOFIA, the Stratospheric Observatory for Infrared Astronomy. Flying high above most of Earth's water vapor, which blocks infrared light, SOFIA-sensitive instruments were aimed at a planetary nebula called NGC 7027, a shell of gas cast off by a dying star. This environment, scientists reasoned, might replicate the conditions of the early universe, a hot, ultraviolet-rich source energizing a surrounding cloud of simple gas. There, etched into the nebula's infrared spectrum, was the unambiguous fingerprint of helium hydride. While this wasn't a detection in the cosmic dawn itself, it was the crucial proof that the molecule could form and persist in space, validating our entire theoretical model of the first chemical steps. The creation of that first molecule was the crack in the dam. Once helium hydride existed, it opened the floodgates for more complex chemistry. Helium hydride itself is a catalyst. It readily reacts with neutral hydrogen, eventually forming molecular hydrogen, or H2. And molecular hydrogen is the true workhorse of early cosmic chemistry. It is far more efficient at cooling than atomic hydrogen because it can rotate and vibrate, releasing energy. This ability to cool is absolutely critical. When a gas cloud can cool, it can contract. This contraction under gravity is what leads to the collapse of dense regions, birthing the second generation of stars and the first true galaxies. Without molecular hydrogen to provide this essential cooling mechanism, the universe might have remained a diffuse soup of isolated gas clouds, unable to build the structures we see today. The first molecules didn't just add new ingredients, they fundamentally changed the physics of how the universe could evolve. From this point, the chemical pathway was set. The deaths of the first massive stars in supernova enriched the cosmos with the first heavy elements: carbon, oxygen, nitrogen, silicon, and iron. These ashes were then incorporated into the next wave of star formation, and around those stars the first dust grains began to form. These microscopic particles of carbon and silicates provided surfaces where atoms could meet and form bonds, a process far more efficient than random collisions in empty space. On these tiny cosmic platforms, chemistry exploded in complexity. Water ice formed on dust grains. Molecules like carbon monoxide became common. Eventually, in the frigid, dark clouds that would collapse to form new solar systems, even more complex organic molecules formed, including the precursors to life itself, amino acids and the building blocks of RNA. Every complex molecule in our bodies, every element heavier than helium, can trace its lineage back to that first, tentative bond between a helium atom and a hydrogen ion in the dark, ancient cosmos. The story of the cosmic dawn is not just one of light overcoming darkness, but of simplicity giving way to complexity, setting the stage for everything that was to follow. But to truly map the distribution of these first luminous objects, we must learn to see their collective, accumulated glow, a faint, cosmic whisper of light that has been traveling since the very beginning. This brings us to the subtle and intricate mystery of the cosmic infrared background. Imagine trying to discern the total light output of every city on Earth by viewing our planet from deep space. You wouldn't see individual skyscrapers or streetlights. You would perceive a faint, patchy glow emanating from the continents, a collective radiance that tells a story of human activity. Astronomers face a similar challenge when looking at the universe's first cities of stars. The combined light from that first generation of galaxies, after traveling for over 13 billion years and being stretched by the expansion of the universe, now arrives as a diffuse, all-pervading background of infrared light. It is the oldest collective glow in the cosmos, a fossil imprint of the very first starlight. This background, however, is not perfectly smooth and uniform. It is filled with subtle irregularities or anisotropies, slightly brighter patches and slightly dimmer voids. These fluctuations are the crucial key. They represent the original clustering of the first stars and galaxies. The brighter patches in the background glow correspond to regions of the early universe where structure formation was more advanced, where more proto-galaxies had gathered and ignited their first stars. The dimmer areas map onto the primordial voids, the emptier regions where fewer luminous objects had managed to form. By meticulously mapping the pattern of these anisotropies, astronomers are essentially creating a statistical portrait of the large-scale structure of the universe during the cosmic dawn. It allows them to answer fundamental questions. How clustered were the first galaxies? How quickly did they light up? Did star formation begin everywhere at once, or did it ignite in specific, connected nodes across the cosmic web? The monumental challenge, however, lies in actually detecting and isolating this incredibly faint signal. The cosmic infrared background is not the only source of infrared light hitting our telescopes. It is drowned out by a cacophony of foreground noise that is orders of magnitude brighter. Our own solar system is filled with zodiacal light, sunlight scattered by countless dust particles within the plane of our planetary system. Our galaxy, the Milky Way, glows brightly with infrared light from its own countless stars and vast, dusty clouds. Even the instruments on our telescopes themselves emit a faint thermal infrared glow. Trying to find the cosmic infrared background anisotropies is like trying to hear a single, faint violin note played in the middle of a roaring heavy metal concert. The signal is there, but separating it from the overwhelming noise requires extraordinary precision and clever statistical techniques. Scientists tackle this Herculean task by meticulously observing large, seemingly empty patches of the sky far from the bright plane of the Milky Way. They then use complex models to subtract all the known foreground contributions, the zodiacal light, the faint glow of distant Milky Way stars, the emission from interstellar dust. What remains after this painstaking subtraction should be the extragalactic background light. But even then, the work is not done. This remaining signal contains not only the light from the first galaxies, but also the accumulated light from all later generations of galaxies. The final step is to look for specific patterns in the fluctuations that statistically favor an origin in the very earliest times. It is a detective story written in the language of statistics and probability, a search for a ghostly pattern within a pattern. The initial results from missions like the Spitzer Space Telescope have been tantalizing, suggesting a level of clustering in the background that implies the first galaxies were incredibly bright and efficient at forming stars, a finding that intriguingly aligns with the surprising giant galaxies now being found by the James Webb Space Telescope. Decoding this ancient infrared whisper is our best hope for creating a true population map of the universe's first light, revealing not just the brilliant individuals, but the entire glowing tapestry of the cosmic dawn. To truly map the invisible architecture of the early universe in 3 dimensions, we need to tune our instruments to a very specific, faint cosmic hum, a whisper of radio waves with a wavelength of 21 centimeters, emitted by the most abundant substance in the cosmos, neutral hydrogen. This signal represents one of the most promising, yet most elusive, windows into the cosmic dawn. It is the universe's own detailed diary of its transition from darkness to light, and reading it would be a revolution in cosmology. The physics behind this signal is beautifully elegant. A hydrogen atom consists of a single proton and a single electron. Both particles possess a property called spin, akin to a tiny magnetic field. These spins can be aligned in the same direction or in opposite directions. The opposite alignment is a slightly higher energy state. Very occasionally, an atom in that higher energy state will spontaneously flip its spins, releasing the tiny bit of extra energy as a photon of radio waves with a precise wavelength of 21 centimeters. In the modern universe, this happens so rarely for any single atom that it's almost negligible. but in the early cosmos, where hydrogen was the only thing for billions of light years, the collective sigh of all those atoms flipping should have created a faint but detectable background radio signal. Because this signal is produced by neutral hydrogen, its presence directly maps the distribution of the cosmic fog before and during reionization. The true power of this 21-centimeter signal lies in its Doppler shift. As the universe expands, the wavelength of this light is stretched or redshifted. The amount of stretching tells us exactly how long ago the light was emitted. This means that by tuning our radio telescopes to different frequencies, we are effectively selecting different slices of time. We could, in theory, create a full three-dimensional movie of the early universe, watching in real time as the first bubbles of ionized gas begin to appear around the first stars and galaxies, growing and merging until they finally clear the entire cosmic fog. It would provide an unparalleled view of the timeline and the morphology of reionization, showing us whether it was a slow and steady process or a fast and patchy one. However, detecting this fossil radio whisper is arguably one of the most difficult challenges in all of modern astronomy. The signal is incredibly faint, and over its 13 billion-year journey, it has been stretched from its original 21 centimeters to wavelengths of 2 meters or more, placing it in the low-frequency radio band. This band of the spectrum is catastrophically polluted by human-made radio interference from everything from television broadcasts to satellite transmissions and even aircraft radar. Furthermore, our own galaxy blasts out synchrotron radiation at these same frequencies, which is millions of times brighter than the cosmic signal we're trying to find. It is like trying to hear the faint rustle of a single leaf in a hurricane, but the challenges don't end there. The Earth's ionosphere, a layer of charged particles in our upper atmosphere, acts as a shimmering, turbulent lens that bends and distorts these long radio waves as they pass through, blurring the delicate details of the signal we seek. To overcome this, astronomers have had to become incredibly ingenious. They have built massive radio telescope arrays in some of the most remote, radio-quiet locations on Earth, such as the deserts of South Africa and the outback of Western Australia. Projects like the Hydrogen Epoch of Reionization Array, or HERA, and the Future Square Kilometer Array, or SCAR, consist of hundreds, even thousands, of simple radio antennas working together as a single colossal instrument. Their goal is not to take pretty pictures, but to meticulously measure the subtle fluctuations in the intensity of radio waves across the sky, searching for the specific statistical signature of the 21-centimeter signal buried deep within the overwhelming noise. The data these arrays produce is a mountain of numbers representing complex interference patterns. Sophisticated algorithms and supercomputers are then used to digitally subtract the foreground signals from our galaxy and human activity. This process is like trying to isolate the sound of a single voice in a massive stadium by recording the entire roar of the crowd and then digitally removing every other voice until only one remains. It is a monumental task in data processing, and so far, the definitive signal has remained just out of reach, though the experiments are steadily tightening the constraints on what it must look like. The reward for this Herculean effort will be nothing less than a new cosmic map. Detecting the 21-centimeter signal would allow us to see the detailed structure of the cosmic web when it was just beginning to form, illuminating the role of dark matter with unprecedented clarity. It could reveal the properties of the very first stars and galaxies by showing us the size and distribution of the first ionized bubbles they created. It might even provide clues about the nature of dark energy and the fundamental properties of the universe by allowing us to trace the expansion history with a whole new independent method. This faint radio whisper is a direct line back to the universe's infancy, and we are only just learning how to listen. But to build a vast cosmic web, you need more than just the luminous knots where galaxies cluster. You need the invisible threads that connect them all. This brings us to the 13th mystery of the cosmic dawn, the origin of the filaments themselves. The grand, large-scale structure of the universe resembles a colossal spider's web, with long, delicate filaments of dark matter and gas stretching for hundreds of millions of light years, connecting massive galaxy clusters at their intersections. But how did these faint tendrils, the very scaffolding of the cosmos, first begin to form from the nearly smooth primordial soup? And was their structure dictated solely by the gravitational pull of dark matter, or did the ordinary baryonic matter, the stuff of stars and planets, play an active and significant role in shaping them? The prevailing theory gives dark matter the lead role. As we've discussed, dark matter's gravity created the initial blueprint. The slight overdensities in the dark matter distribution after the Big Bang grew over time, collapsing first into a network of filaments and knots known as the cosmic web. This dark matter scaffold is thought to have formed first, providing the gravitational potential wells into which the normal matter later flowed. In this model, the baryonic gas was essentially a passive passenger, simply following the gravitational roadmap laid out by the dark matter. The filaments would have been in place long before the gas within them became dense enough to cool, fragment, and eventually form stars and galaxies. However, this simple story of a dark matter-driven process is being challenged. There's growing evidence that ordinary matter might have played a much more active part through a complex interplay of physics that goes beyond mere gravity. As gas falls into the dark matter filaments, it doesn't just flow smoothly. It can shock heat to incredibly high temperatures, creating a searing plasma that actually contributes significant pressure. This hot gas can then feed back on the structure, potentially altering the dynamics of how the filament evolves. Furthermore, the immense energy pouring out from the first galaxies and quasars, the same energy that drove reionization, could have reheated the gas within these filaments, preventing it from cooling and collapsing efficiently. This means the ordinary matter wasn't just along for the ride. Its own thermodynamic properties and the powerful influences of early astrophysical sources may have helped sculpt the final form and density of the cosmic web's threads. So how do we possibly observe these faint, primordial structures to distinguish between these theories? We cannot see the dark matter directly, and the gas in the filaments is often too diffused to emit much light on its own. Astronomers must therefore become cosmic detectives using indirect but brilliant methods. The most powerful tool is once again the light from distant quasars. As this brilliant light travels through the universe on its way to us, it passes through these intergalactic filaments. The sparse gas within the filaments, while not luminous, is not entirely empty. It contains a population of neutral hydrogen atoms. These atoms will absorb specific wavelengths of the quasar's light, creating a forest of absorption lines in its spectrum. By analyzing the patterns of these lines, their strength, their spacing, their redshift scientists can reconstruct the density, temperature, and distribution of the gas in the filaments that the light passed through. It's like using a distant lighthouse to illuminate the fog banks around otherwise invisible islands, revealing their shape and size by the pattern of light they block. The hunt is now on to find the very earliest, most pristine filaments, those that existed before they were heavily processed by galaxies and black holes. The James Webb Space Telescope and large ground-based observatories are searching for the most distant quasars and galaxies possible. By studying the absorption lines imprinted on their light, we can peer back to a time when the cosmic web was still under construction. If we find that the filaments at these extreme redshifts already have a structure that perfectly matches the predictions of dark matter, only simulations, it would strongly support the idea of dark matter as the sole architect. But if we find evidence that the filaments are smoother, hotter, or more disrupted than those simulations predict, it would be a clear sign that baryonic physics, the heating and feedback from the first stars and galaxies, was already significantly influencing the cosmic web structure during the cosmic dawn itself. Tracing these primordial threads is about more than just mapping the universe. It's about understanding the complete and complex partnership between the visible and invisible components of reality, a collaboration that built the largest structures in existence. Following the fading brilliance of the cosmic microwave background, the universe entered its most silent and uneventful chapter, a profound epoch of darkness known as the Dark Ages. This was not a period of dramatic events or brilliant objects, but rather a deep cosmic stillness, a long, quiet breath held in the dark. The central mystery here is one of duration. Precisely how long did this era of absolute blackness last? Was it a relatively brief interlude, or did the universe languish in this formless state for an astonishingly long time before the first sparks of starlight finally pierced the void? Pinpointing the length of this quiet period is far more than a matter of cosmic chronology. It is a direct measurement of how quickly the infant universe could overcome its own initial smoothness and begin the magnificent process of building complexity. To understand why this duration is so telling, we need to consider the initial conditions. The cosmic microwave background shows us a universe that was incredibly smooth, with density variations of only about 1 part in 100,000. These tiny ripples are the seeds of all future structure, but they needed time to grow. The Dark Ages represent that crucial incubation period where gravity, working primarily through the invisible scaffolding of dark matter, was silently and patiently amplifying these minute imperfections. The length of this era directly reflects the strength of the initial seeds and the efficiency of gravity's pull. A shorter Dark Ages would imply that the primordial fluctuations were stronger than we think, or that some other unknown mechanism gave structure formation a helping hand. A longer period of darkness would suggest the opposite, that the initial seeds were even fainter, and that gravity had to work for a much longer time before the first collapses could occur. Our ability to measure this duration comes from a few key, yet incredibly challenging observations. The most significant constraint comes from the most distant objects we can detect. When we find a galaxy or a quasar at a certain redshift, we know that by that point in time, the Dark Ages had to have ended. The current record holders are galaxies observed by the James Webb Space Telescope that existed when the universe was only around 200 million years old. Their mere presence tells us that the Dark Ages concluded by at least that time. The other major constraint comes from the study of reionization. Since the process of reionization was fueled by the light from the first stars and galaxies, its beginning marks the definitive end of the Dark Ages. Observations of the cosmic microwave background from the Planck satellite suggest the process was well underway by the time the universe was around 450 million years old, and the Hubble Space Telescope's observations of early galaxies suggest it may have started even earlier. This gives us a bracket. The Dark Ages ended somewhere between 200 million and 450 million years after the Big Bang. But that is a window of over 200 million years, a vast span of time on a cosmic scale. Narrowing it down further is the true challenge. The most promising method is the hunt for a definitive spectroscopic signature of a completely neutral universe. This is the goal of the 21-centimeter experiments we discussed. If they can detect the moment when the absorption signal from neutral hydrogen begins to show the first patches of emission indicating the formation of the first heated regions around stars, they will have pinpointed the end of the Dark Ages with incredible precision. Until then, this quiet period remains one of the least observationally accessible, yet most fundamentally important chapters in our cosmic history. Its duration holds the secret to the initial momentum of creation itself, a silent timer that started at the Big Bang and stopped with the birth of the very first star. And as the first galaxies began to coalesce and grow, a new and deeply fascinating possibility emerges from the chaos of the early cosmos: the potential existence of binary supermassive black holes, two gravitational titans locked in a close orbital dance. These would not be the stellar mass black hole pairs we've detected through gravitational waves here in the modern universe. We're talking about pairs of monsters, each weighing millions or even billions of times the mass of our Sun, orbiting one another in the hearts of the very first galaxies. The idea that such incredibly complex and massive systems could have formed during the cosmic dawn pushes our models of structure formation to their absolute limits and opens up a thrilling new window into the dynamics of the infant universe. The most straightforward path to forming these binaries is through the hierarchical merging of galaxies, a process we believe was rampant in the dense early universe. Imagine two of the earliest proto-galaxies, each having formed its own massive black hole at its center through one of the mechanisms we've discussed. Perhaps a direct collapse black hole or the remnant of a massive population 3-star. As these young galaxies drift through space, their immense dark matter halos exert a gravitational pull on each other, drawing them closer over millions of years. They eventually collide and merge, forming a larger, combined galaxy. In this violent merger, the two central black holes are dragged along with their host galaxies toward the new common center of gravity. As they sink through the dense gas of the merged galaxy, dynamical friction, a kind of gravitational drag, slows them down, causing their orbits to decay. They eventually form a bound pair, a supermassive black hole binary, circling each other in the galactic core. In the crowded environment of the early universe, where galaxies were packed closer together, this entire process might have happened with astonishing speed, potentially creating binaries far earlier than we ever thought possible. The existence of such pairs would have profound implications. Firstly, they would be the most powerful engines of gravitational waves in the universe. As a binary pair orbits, they radiate energy away in the form of ripples in spacetime itself. This causes their orbits to slowly shrink over eons, bringing them closer and closer together until they eventually merge in a cataclysmic event that would unleash a titanic burst of gravitational waves. Detecting the low-frequency hum from a population of these circling giants in the early universe would provide a completely new way to map cosmic history, offering a direct probe of the merger rate of the first galaxies. Furthermore, the environment around a supermassive binary would be a cauldron of unimaginable physics. The gravitational forces at play could slingshot stars at incredible velocities, rip apart gas clouds, and funnel material into dazzlingly bright accretion disks around each black hole, creating a light show that would dwarf anything a single black hole could produce. However, a major theoretical hurdle known as the final parsec problem questions whether these pairs could ever actually get close enough to merge. As the black holes orbit each other, they need to shed orbital energy to get closer. Dynamical friction from stars and gas is efficient at first, but once they reach a separation of about 1 parsec, roughly 3.26 light-years, this process becomes ineffective. The binary could essentially stall at this distance, remaining in a stable, long-lasting orbit without ever coming close enough to merge via gravitational wave emission. For a binary to overcome this final parsec and merge, it needs a constant supply of stars or gas to interact with and drain its orbital energy. Whether the gas-rich, turbulent centers of the first galaxies provided this necessary environment is a wide-open question in astrophysics. Finding evidence for these binaries in the cosmic dawn would therefore be nothing short of revolutionary. It would not only confirm that galaxy mergers were a primary driver of growth in the early universe, but would also provide a natural explanation for how some black holes grew to such immense sizes so quickly through a chain of successive mergers. The most promising way to find them is by looking for the unique periodic flickering in the light of distant quasars. If a quasar is powered by a binary black hole, the orbital motion can cause a regular, predictable modulation in its brightness as the black holes eclipse each other or as their individual accretion disks interact. New observatories like the Laser Interferometer Space Antenna, or LISA, a planned space-based gravitational wave observatory, are specifically designed to detect the low-frequency ripples from merging supermassive black holes. If LISA were to detect a signal from a merger that occurred in the first billion years of the universe, it would be definitive, ground-shaking proof that the cosmic dawn was not just an era of first light, but also an era of first unions where the greatest monsters in the cosmos found their partners and began a dance that would shape the galaxies for billions of years to come. Yet, even as the first molecular bonds were forming, another, more solid kind of chemistry was beginning to seed the cosmos, creating the microscopic building blocks of future worlds. This is the story of the very first cosmic dust, a mystery that touches on the origin of everything from planets to life itself. In our modern universe, dust is everywhere, tiny solid grains of carbon and silicates floating in the space between stars, gathering in vast, dark clouds that will one day collapse to form new solar systems. But in the pristine aftermath of the Big Bang, there was no dust at all. The universe was a gas-only affair with no solid materials, no microscopic seeds for planets to form around, and no surfaces for complex chemistry to occur. The creation of that first speck of solid matter was a revolutionary moment, a transition from a purely gaseous cosmos to one that could eventually build rocky planets and nurture the chemistry of life. The question of where these first dust grains came from leads us directly to the most violent and creative events of the cosmic dawn, the deaths of the first massive stars. A leading theory points to the incredible shockwaves and expanding ejecta of supernova explosions as the primary cosmic factories. In the furious aftermath of a star's death, a vast cloud of newly forged heavy elements is blasted outward at tremendous speeds. As this expanding shell of hot gas races into space, it eventually cools enough for atoms to begin sticking together. Atoms of carbon, silicon, oxygen, and iron, forged in the star's final moments, collide and bond, first into tiny clusters and then into microscopic solid grains. It's a process akin to soot forming in a candle flame, but on a cosmic scale, with a single supernova potentially seeding entire galaxies with trillions upon trillions of these precious dust particles. But supernova might not have been the only source. Another fascinating possibility lies in the outer atmospheres of certain types of aging, massive stars before they ever go supernova. In these cool, extended stellar envelopes, conditions can be just right for atoms to condense directly out of the gas phase onto pre-existing seed nuclei, growing dust grains like frost forming on a window pane. This process could have begun sprinkling dust into the cosmos even before the most massive stars ended their lives, providing an early, continuous source of solid material. There's even the exotic possibility that some dust formed in the dense, windy outflows from the accretion disks around the first supermassive black holes, adding another layer of complexity to the story. Understanding which process dominated is crucial because each leaves a different chemical signature. Dust formed in the violent, oxygen-rich environment of a supernova blast might be rich in silicates and oxides like tiny grains of sand or rust. Dust that condenses more gently in the carbon-rich atmosphere of an aging giant star would likely be composed mostly of graphite and other forms of carbon, more like microscopic diamonds or soot. The type of dust available in the early universe would have directly influenced the chemistry of the second generation of stars and the planets that formed around them. This is where the James Webb Space Telescope becomes an indispensable detective. Dust, by its very nature, is incredibly effective at absorbing visible and ultraviolet light from hot, young stars. But it doesn't destroy that energy, it re-radiates it at much longer infrared wavelengths. JWST powerful infrared eyes are perfectly designed to detect this warm glow of ancient dust. When it looks at the most distant, earliest galaxies, it isn't just looking for starlight. It's analyzing the spectrum of that light for the specific telltale dip caused by dust absorption. The amount of dust reddening the light of a galaxy tells us how dusty it already was. Furthermore, by detecting the specific infrared emission features from silicate and carbon-based grains, JWST can act as a cosmic geologist, identifying the actual mineral composition of the dust in these pioneer galaxies. The initial findings have been startling. JWST has already observed dust in galaxies that existed when the universe was less than 5% of its current age. The sheer amount of dust present at such an early time is challenging our models. It suggests that dust production must have been incredibly efficient and rapid, perhaps requiring an entire population of supernova to go off in quick succession, or pointing toward alternative, more efficient dust formation channels that we haven't yet considered. Each dusty galaxy observed by Webb is a time capsule, preserving a record of the first solid materials ever created. By studying them, we are tracing the origin of the very stuff that would one day coalesce into Earth-like planets and become the foundation for all the complexity that followed, turning the universe from a simple expanse of gas into a place capable of building worlds. But to truly understand the profound transformation of the cosmic dawn, we must pull back and consider the universe's grandest vital sign, its temperature. The story of the cosmos is in many ways a story of cooling down and heating up, a thermal history written in the fading glow of the Big Bang and the explosive birth of the first stars. This temperature evolution is our 17th mystery, a sweeping narrative of how the universe went from a state of uniform, cold darkness to being patchily reheated by its first luminous objects, fundamentally altering its chemical and physical state forever. After the brilliant flash of the Big Bang faded into the cosmic microwave background, the universe entered a long period of quiet, passive cooling. As space itself expanded, it stretched the wavelength of the leftover radiation, causing its effective temperature to steadily drop. Think of it like a cup of coffee left on a counter. It naturally cools down as its heat radiates away into the surrounding room. For millions of years, this was the universe's only story, a slow, inexorable cool-down from a searing plasma to a cold, neutral gas. The cosmic microwave background radiation, which started at thousands of degrees, had cooled to a mere few tens of degrees above absolute zero. The hydrogen gas that filled the cosmos, having decoupled from the radiation, was cooling even faster, sinking to a deeply frigid state only a few dozen degrees above absolute zero. The universe was not just dark, it was growing cold and still, a vast and silent thermodynamic engine slowly winding down. This deep chill, however, could not last forever. The very first stars and black holes were destined to become the universe's first furnaces, violently reversing this billion-year-long cooling trend. The moment the first population 3 star ignited, it did more than just produce light. It flooded its immediate surroundings with high-energy ultraviolet photons. This radiation didn't just ionize hydrogen, it also heated it, dramatically raising the temperature of the local gas from a frigid few dozen degrees to a searing 10,000 degrees or more. It was a localized thermal explosion, creating the first hot bubbles in the cold cosmic soup. Similarly, the first active black holes, blazing as mini-quasars, poured out even more intense X-ray radiation. X-rays have an incredible ability to travel vast distances through neutral gas before being absorbed, meaning they could heat the diffuse hydrogen in the vast voids between galaxies, raising the temperature of the entire intergalactic medium in a widespread background fashion. This wasn't just a local event, it was the beginning of a universal reheating, a process that would eventually end the cold dark ages and set the stage for all future galaxy formation. This complex interplay of cooling and heating created a new and dynamic thermal landscape. The universe was no longer a uniform, cold place. It became a patchwork of extreme temperatures, blisteringly hot bubbles of ionized plasma around stars and galaxies, connected by vast tracts of warm, X-ray heated gas, all set within a remaining background of still neutral cold hydrogen. This patchiness is a critical clue. The pattern of hot and cold regions is a direct record of the timing and the distribution of the first energy sources. By mapping this fossil temperature distribution, we could effectively create a thermal image of the universe during its adolescence, revealing where the first stars clustered and how efficiently their energy propagated through the primordial gas. So how do we possibly take the temperature of the universe 13 billion years ago? Our most powerful thermometer is once again the 21-centimeter line from neutral hydrogen. The beauty of this signal is that its strength is exquisitely sensitive to the gas's temperature. When the background radiation temperature matches the gas temperature, the absorption signal vanishes. But if the gas is colder than the background radiation, it will appear in absorption, sucking photons out of the background. If the gas is hotter, it can actually add photons, creating an emission signal. By searching for the subtle fluctuations in the 21-centimeter signal across the sky at different redshifts, radio astronomers can create a three-dimensional map of the gas temperature during the cosmic dawn. Finding a patch of absorption would indicate a region of cold, neutral gas untouched by the first stars. A patch of emission would reveal a region that had already been heated by a nearby star or black hole. This would allow us to literally watch the heating fronts expand and merge, charting the end of the cold era in real time. There is another, even more subtle way to detect this reheating, etched into the oldest light we can see, the polarization of the cosmic microwave background. As the first bubbles of ionized plasma formed during reionization, the free electrons within them could scatter the passing CMB light. This scattering process tends to polarize the light, imprinting a specific large-scale pattern on it. The precise characteristics of this polarization pattern, its E-mode signature, encode information about the timing and the duration of reionization. A sudden, rapid reheating would leave a different fingerprint than a slow, gradual one. Missions like the Planck satellite have already detected this polarization signal, and its statistical properties suggest reionization was a relatively extended process, consistent with a universe being gradually reheated by the first populations of stars rather than being abruptly blasted by a few brilliant quasars. Future observatories like the Simons Observatory and CMB-S4 will measure this polarization with even greater precision, hoping to read the full thermal history of the universe's adolescence in the faint afterglow of its birth. Imagine a spectacle of cosmic violence so immense it would dwarf any explosion in the modern universe, the death of a population 3-star. These primordial behemoths, hundreds of times more massive than our Sun, were destined for lives that were spectacularly short and conclusions that were unimaginably violent. Their supernova explosions were not merely the end of a star, they were the primary forges in which the recipe for the entire complex cosmos was written. The nature of these cataclysms, the unique elements they created, and the lasting scars they left on the gas that would form the next generation of stars, represents one of the most dynamic and consequential mysteries of the cosmic dawn. These were not your typical supernova. The pure hydrogen and helium composition of a population 3-star meant its internal nuclear furnace operated under entirely different rules. Without heavier elements to help regulate its energy production and provide stability, such a massive star would burn through its fuel at a ferocious rate, living for only a few million years before its core inevitably collapsed. But the type of explosion that followed is still a subject of intense scientific debate. For the very largest of these giants, the collapse might have been so complete and so powerful that it created a hypernova, a supernova on steroids, unleashing energies 100 times greater than typical stellar explosions. Some theories even suggest that the entire star might have collapsed directly into a black hole without a traditional supernova at all, or that its death throes produced incredibly long-duration gamma-ray bursts, focusing the explosive energy into narrow, universe-spanning jets that could sterilize entire galaxies. The specific mechanics of their demise determined not only how much energy they injected into the early cosmos, but also exactly which new elements were cast out into the void. This act of cosmic alchemy, known as nucleosynthesis, was profoundly unique. In the hearts of these stars and in the incredible shockwaves of their explosions, the first atoms heavier than helium were painstakingly forged. But the yield was strange and exotic. Because the initial fuel was pure, the nuclear reaction chains could proceed down pathways that are impossible in later, metal-enriched stars. This likely produced a very distinct chemical signature, a peculiar abundance pattern of elements that is the key fingerprint of a population 3 explosion. We expect these supernovae to have been incredibly efficient producers of certain elements like oxygen, silicon, and neon. But they might also have been poor producers of iron compared to later supernovae, or they might have created unusual ratios of elements like carbon and nitrogen. Some models even predict the production of rare, radioactive elements that no longer exist in the universe today, which would have decayed away long ago but left a temporary, radioactive glow that could have briefly outshone the entire host galaxy. The specific elemental cocktail they produced set the initial chemical conditions for everything that followed, a foundational recipe that was then blended and diluted by billions of years of subsequent stellar generations. The impact of such an explosion on its local environment was nothing short of transformative. Imagine a vast, calm cloud of pristine primordial hydrogen and helium, quietly on the verge of gravitational collapse. Suddenly, from a single point, a wave of unimaginable energy and a storm of newly forged radioactive elements slams into it. The immediate effect would have been utterly destructive. The shockwave would have heated the gas to millions of degrees, blowing it apart and preventing any further star formation in that region for millions of years. It might have even torn apart nearby protogalactic clumps of dark matter, completely disrupting the early growth of structure. But on a longer timescale, this violent act was also deeply creative. The expanding supernova remnant would eventually slow down and cool, sweeping up enormous amounts of gas and dust into a dense, heavy shell. This shell, now enriched with the first heavy elements, became the perfect nursery for the next generation of stars. Furthermore, the blast wave itself could trigger new star formation by compressing other distant gas clouds to the point of gravitational collapse. It was a cycle of creation through destruction, where the death of one stellar titan paved the way for the birth of countless smaller, longer-lived stars. The most tantalizing part of this mystery is that we may still be able to find the chemical ghosts of these first explosions living among us. Astronomers are on a dedicated hunt for the oldest stars in our own Milky Way galaxy, stellar relics that formed from the still pristine, minimally enriched gas shortly after the cosmic dawn. These ancient stars, known as ultra-metal-poor stars, are the time capsules we need. They contain within their atmospheres the preserved chemical abundance patterns of the gas cloud from which they formed. By pointing our most powerful spectrographs at these faint, old stars, we are effectively conducting a forensic chemical analysis of the supernova that preceded them. The goal is to find a star whose elemental pattern is bizarre, perhaps one with a huge amount of carbon and oxygen but almost no iron, or one with a strange overabundance of a single rare element. Such a pattern would be the long-sought fingerprint of a single, specific type of population 3 supernova, a direct chemical message from the universe's first and greatest fireworks display. Finding just one such star would allow us to reverse engineer the mass and the explosion mechanism of the very first stars, turning a theoretical mystery into a documented historical event and giving us a direct window into the violent processes that seeded the cosmos with the ingredients for planets and life. Orbiting the halo of our own Milky Way galaxy are some of the most ancient and mysterious objects in the entire cosmos, globular clusters. These are immense spherical swarms of hundreds of thousands of stars, all bound together by gravity in a space that is incredibly small by cosmic standards. To stand on a hypothetical planet inside one, the night sky would be ablaze with tens of thousands of stars brighter than Venus, a dazzling, perpetual celestial festival. But the true wonder of these clusters isn't their beauty, it's their profound age. We know from detailed observations that the stars within them are among the oldest in the universe, composed almost entirely of hydrogen and helium with only the barest traces of heavier elements. This pristine chemical composition is the crucial clue that points their birth directly back to the cosmic dawn, making them living fossils from the universe's infancy. The central mystery is not if they are old, but how such incredibly dense and massive structures could have formed so quickly in the first place, and what they can tell us about the conditions of the early universe that simply don't exist today. The leading theory for their formation is a scenario of incredible intensity, a perfect storm of conditions unique to the early cosmos. Imagine a region of the early universe where the dark matter and gas were slightly denser than average. As this region begins to collapse under its own gravity, it draws in a tremendous reservoir of pristine, cold hydrogen and helium gas. In the modern universe, such a collapsing cloud would be rich with dust and heavy elements, which allows it to fragment efficiently into many separate stars of varying sizes. But in the primordial environment, without this efficient cooling, the physics changes entirely. The gas cannot fragment as easily, leading to a runaway collapse where an enormous amount of material funnels into a very small volume. This triggers a ferocious single burst of star formation, a starburst of unbelievable efficiency that converts nearly all of the available gas into stars in one frantic, concentrated event. The result is not a loose association of stars, but a densely packed, gravitationally bound cluster of hundreds of thousands of stars, all born at roughly the same time from the same cloud of pure primordial gas. However, this is not the only compelling idea on the table. A fascinating alternative theory suggests that at least some of these ancient clusters may not have formed on their own, but instead began their lives as the very hearts or nuclei of small dwarf galaxies. In this scenario, a small proto-galaxy forms early on, with a concentrated clump of stars at its center. Over billions of years, as this dwarf galaxy orbits a larger galaxy like the Milky Way, the relentless tidal forces, the difference in gravity between the near and far side of the small galaxy would slowly but mercilessly strip away its outer layers of stars and gas. What remains after this cosmic stripping process is complete is just the dense, resilient core, a globular cluster. This would explain why we see objects like the spectacular Omega Centauri that have some properties of a disrupted galaxy core, such as a spread in the ages of its stars and a complex internal structure, unlike the simple, single-age population of a classic cluster. A third, and perhaps most revealing, possibility is that these clusters are the sole surviving relics of the very first star-forming environments. Their incredibly low metallicity suggests they formed from gas that was never polluted by the ashes of previous supernova. This is a critical point. If a cluster formed from gas that had been enriched by even a single generation of stars, those stars would contain measurable amounts of heavy elements. The fact that the stars in the oldest clusters do not suggest they might be genuine population 2 stars, forming from gas that was seeded only by the very first, incredibly rare and massive population 3 supernova, or perhaps even from gas that had witnessed no supernova at all. This would make them our closest available proxy for studying the first stellar generations, pristine time capsules preserving the physical conditions of the earliest star-forming clouds. Unraveling which of these origin stories is correct or whether all 3 played a role is a major focus of modern astronomy, and the James Webb Space Telescope is poised to be the ultimate arbiter. By peering back to the cosmic dawn itself, Webb is not just looking for the first galaxies, it is also searching for infant globular clusters in the process of formation. It has the power to see if they are forming in isolation within vast dark matter halos, or if they are always seen as bright knots within larger, nascent galaxies, which would support the nuclear origin theory. Furthermore, by using its powerful spectrographs to analyze the light from the oldest clusters in our own galaxy, astronomers can perform a detailed chemical autopsy on their individual stars. If all the stars in a cluster show an identical, simple chemical pattern, it points to a single, rapid burst of formation. If, however, some stars show slight variations, tiny amounts of elements that could only be forged in a supernova, it suggests the cluster might have witnessed multiple, slightly spaced-out episodes of star formation, a hallmark of a more complex galactic origin. These dense stellar cities are not just beautiful relics, they are history books written in starlight, and we are only now learning how to turn their pages to read the story of the universe's first structures. To truly grasp the origin of the cosmic web and the very first galaxies, we must journey back to a time even more remote than the cosmic dawn, to a fleeting moment of incomprehensible expansion that set the entire stage for everything to come. This is the epoch of cosmic inflation, a theoretical period when the universe is thought to have expanded by an unimaginable factor in a fraction of a second immediately after the Big Bang. While this event occurred an eternity before the first stars flickered to life, its fingerprints are believed to be imprinted on the large-scale structure of the cosmos we see today. The profound mystery lies in connecting the grand, exponential growth of inflation directly to the minuscule seeds that would one day grow into galaxies, and asking whether the distribution of those first structures can tell us something about inflation that we cannot learn any other way. The most crucial legacy of inflation is its proposed solution to the universe's initial conditions. The cosmic microwave background shows us a universe that is remarkably uniform, but with tiny, faint ripples in density. Inflation explains the origin of these ripples by stretching microscopic quantum fluctuations, those tiny, random jitters that exist even in a vacuum to astronomical sizes. Imagine a tiny, subatomic patch of space where the energy density is ever so slightly higher than its surroundings due to a random quantum event. Inflation would then take that minuscule patch and inflate it to a scale larger than our entire observable universe. What was once a quantum fluctuation becomes a classical density fluctuation, a region of space that is slightly denser than average. It is within these over-dense regions, these gravitational seeds scattered across the cosmos by inflation's immense stretching, that dark matter would later begin to gather, eventually pulling in normal gas to form the first stars and galaxies billions of years later. In this way, the largest structures we see today may have their ultimate origins in the smallest possible quantum vibrations. This incredible idea transforms the distribution of the first galaxies into a potential archaeological record of the inflationary epoch. The specific pattern of how galaxies are clustered across the sky, whether they tend to clump together in certain ways or prefer specific distances from one another, is not random. It is a fossilized imprint of the initial spectrum of those quantum fluctuations. The statistical properties of this clustering, such as whether the fluctuations were perfectly random or had subtle correlations, can reveal the specific physics of the inflationary field that drove the expansion. Different models of inflation driven by different types of hypothetical particles or fields predict slightly different patterns for these initial fluctuations. By meticulously mapping the distribution of the most ancient galaxies we can find, we are effectively reading the blueprint that inflation left behind, a blueprint that has been faithfully enlarged and preserved by 13 billion years of gravitational evolution. The James Webb Space Telescope is now conducting this ultimate cosmic census, peering back to chart the precise positions and densities of the first galaxies. By comparing this three-dimensional map to the predictions of various inflationary models, cosmologists hope to perform a direct test of inflation's details. For instance, some models predict that the initial fluctuations should be exactly scale invariant, meaning the relative contrast between dense and sparse regions is the same on all physical scales. Others predict tiny deviations from this perfect scale invariance, which would manifest as a specific preference for galaxy clusters of a certain size. The distribution of the earliest galaxies is our cleanest window into these statistics because they have been influenced by gravity for the shortest amount of time, preserving the primordial pattern with the least amount of contamination from later cosmic events like galactic mergers and collisions. This connection offers a possibility that is both thrilling and humbling. The arrangement of the first brilliant islands of light in the cosmic dark may hold secrets about the universe's first moment of existence, a connection spanning from the quantum realm to the galactic scale. If the pattern encoded in the cosmic dawn aligns with a specific inflationary model, it would provide stunning evidence for a theory that is currently beyond our direct observational reach. It would mean that by studying the dawn of structure, we are not just learning about the birth of stars, but also about the very birth of spacetime itself, glimpsing the physics that set our entire reality into motion. When we observe the majestic spiral galaxies of today, like our own Milky Way, we see a well-ordered cosmic dance. Their vast arms, filled with stars and gas, rotate around a central hub with a stability that speaks to billions of years of gravitational evolution. It's a serene and predictable motion, but when we point our most powerful telescopes back to the cosmic dawn, that sense of order begins to break down. We find galaxies that are anything but serene. They are chaotic, turbulent, and often surprisingly disordered in their motion. This leads us to a profound puzzle about the infant cosmos, the mystery of early galaxy rotation. How did the first galaxies acquire their spin, and why do their rotation patterns look so different from the elegant spirals we see around us today? The answer is written in the language of angular momentum, a fundamental property of the universe that had to be carefully conserved from the largest scales down to the very first collapsing clouds of gas. To understand this, we have to go back to the very beginning of structure itself. The current cosmological model tells us that the initial seeds for all structure were planted by inflation, which left behind tiny ripples in the density of the universe. As these ripples grew under the relentless pull of gravity, they didn't just collapse straight inward. The universe was also expanding, and this created a subtle shearing effect. Think of an ice skater pulling their arms in to spin faster. As vast clouds of dark matter and gas were drawn inward by gravity, any tiny initial motion was amplified, imparting a slow spin to these gigantic collapsing halos. This spin, this angular momentum, is a cosmic inheritance, a fundamental property that was locked into the dark matter scaffolding of the universe from its earliest moments. The dark matter halos that would host the first galaxies were therefore born with a natural tendency to rotate, but here's where the mystery deepens. When we use instruments like the Atacama Large Millimeter Array or ALMA to study the gas within these incredibly distant young galaxies, we don't always see the clean, ordered rotation we might expect. Instead, the observations often reveal a mess. Some early galaxies show signs of rapid, disordered rotation. Their gas is swirling, but not in a stable disk. It's more like a chaotic whirlpool with different parts moving at vastly different speeds and directions. Other galaxies appear to be barely rotating at all, instead showing signatures of massive, chaotic inflows of gas raining down from the cosmic web, or outflows blasting outward from intense starbursts. This turbulence suggests that the early universe was a far more violent and dynamic environment than we ever imagined, where the simple rules of angular momentum were fighting against a host of other powerful forces. The key to unraveling this chaos lies in understanding the journey of the gas. While the dark matter halo acquired its spin from the large-scale gravitational collapse, the normal baryonic gas had a much more eventful trip. As it fell into the gravitational well of the dark matter halo, it didn't flow smoothly. It crashed into other streams of gas, creating shock waves that heated it to extreme temperatures. In this hot, pressurized state, the gas couldn't easily settle into a stable, rotating disk. It was like trying to form a spinning vortex in a pot of boiling water. The thermal energy overwhelmed the orderly motion of rotation. Furthermore, this gas was not only fighting its own turbulence, but also the powerful feedback from the very stars it was trying to form. The first supernova would have blasted through these nascent disks, violently stirring up the gas and disrupting any fragile rotation that had begun to establish itself. This constant bombardment meant that it could take hundreds of millions of years for a galaxy to settle down, cool off, and finally form the thin, orderly rotating disks that become the majestic spirals we know. The incredible resolution of the James Webb Space Telescope is now allowing us to see this process in unprecedented detail. By not just detecting these early galaxies but dissecting their light with spectroscopy, Webb can map the velocity of their gas. It can show us which parts are moving toward us and which are moving away, creating a detailed map of their internal motions. These velocity maps are revealing that the early universe was a diverse laboratory of galactic dynamics. Some galaxies show the classic signature of a rotating disk, albeit a thick and wobbly one. Others show no clear rotation at all, their dynamics dominated by random motions. And still others show evidence of massive mergers, where two galaxies have collided and their distinct angular momenta are violently interacting, creating a terribly disordered system. This diversity tells us that there was no single path to forming a galaxy. The process was messy, competitive, and heavily influenced by a galaxy's immediate environment and its history of interactions. Ultimately, the rotation of a galaxy is a testament to a grand cosmic balancing act. It's the story of how gravity pulls gas in, how angular momentum tries to spin it out, and how thermal pressure and stellar feedback try to blow it apart. The final structure of a galaxy is a fossil record of which of these forces won out during its formative years. By studying the rotation of the most distant galaxies, we are effectively measuring the initial conditions of the universe's angular momentum and watching how those first spins were transformed by the complex physics of gas, stars, and dark matter. Each chaotic, swirling disk of primordial gas is a snapshot of the universe learning how to build order from chaos, a crucial step on the long road to forming the stable, beautiful galaxies that would one day host stars like our own Sun and planets like our own Earth. But if we hope to find the faintest whispers of magnetism from the dawn of time, we must first learn to listen through a hurricane of modern noise. The quest to detect these primordial fields is one of the most technically daunting challenges in all of modern cosmology, a delicate exercise in extracting an impossibly faint signal from an overwhelming sea of interference. The primary tool for this hunt is the phenomenon of Faraday rotation, a subtle effect that occurs when polarized light travels through a magnetized medium. The magnetic field causes the plane of the light's polarization to slowly twist or rotate, like a needle turning on a compass. The amount of this rotation tells us about the strength of the magnetic field and the density of the material it's passing through. To use this effect, astronomers turn to the universe's most brilliant beacons, distant quasars. By measuring the polarization of a quasar's light and carefully analyzing how that polarization has been rotated at different frequencies during its billion-year journey to Earth, scientists can work backwards to map the magnetic fields that imprinted themselves along the line of sight. The goal is to find a signature of magnetization that exists in the truly empty voids between galaxies, far from any possible galactic dynamo, which would be the smoking gun for a field that is truly primordial and woven into the fabric of space itself. The challenge, however, is that space is not empty, and every step of this measurement is fraught with difficulty. The intergalactic medium is not a perfect vacuum. It is filled with an incredibly diffuse plasma of free electrons. These electrons are essential for the Faraday effect to work, but they are also notoriously difficult to map with precision. Furthermore, the polarized light from the quasar itself must pass through the magnetic fields of our own Milky Way galaxy, which are millions of times stronger than the primordial signal we're trying to detect. This creates a massive foreground contamination that must be modeled and subtracted with incredible accuracy. It's akin to trying to measure the gentle pressure of a single snowflake landing on your hand while you are standing in the middle of a blizzard. Even the most sophisticated observations from the world's largest radio telescopes, like the Very Large Array, have so far only been able to place upper limits on the strength of any intergalactic field. The definitive, unambiguous detection remains tantalizingly out of reach. Another promising avenue is to search for the imprint of these early magnetic fields on the cosmic microwave background. The theory is that a primordial magnetic field would have created tiny amounts of polarization in the CMB through a process called gravitational lensing. The field would have affected the motion of ions in the primordial plasma, creating minuscule swirls and vortices that would leave a unique curly pattern known as B-mode polarization on the ancient light. This signal would be incredibly faint, but if detected, it would be direct, incontrovertible proof of magnetism in the universe's infancy. The hunt for this specific pattern is a primary goal of next-generation CMB observatories like the Simons Observatory and the upcoming CMBS-4 project. These instruments employ arrays of thousands of superconducting detectors, cooled to a fraction of a degree above absolute zero, to measure the CMB's temperature and polarization with microscopic precision. They are looking for a signal that is predicted to be over 1 million times fainter than the temperature variations we see in the famous CMB map. Yet here, too, the challenges are immense. The specific B-mode polarization pattern that could be created by primordial magnetic fields is tragically similar to the pattern that would be created by gravitational waves from the inflationary epoch. Disentangling these two potential signals is a problem that keeps cosmologists awake at night. Furthermore, our own galaxy again pollutes the signal. Dust grains in the Milky Way, when aligned by the galaxy's magnetic field, can emit polarized light that perfectly mimics the B-mode pattern we are desperately searching for in the CMB. This requires these sensitive telescopes to not only observe the sky but to do so at multiple frequencies, carefully mapping and subtracting this galactic foreground with painstaking accuracy. The fact that a definitive detection has not yet been made is not for a lack of trying. It is a testament to the exquisite faintness of the signal and the monumental difficulty of the experiment. Each new observation tightens the constraints, telling us what the magnetic fields could not have been like, slowly narrowing the possibilities until, one day, the ghost of the universe's first magnetism may finally reveal itself. This anticipated dip is far more than a simple fluctuation in a radio signal. It is a direct cosmic thermometer and a timeline, a specific fingerprint left by the universe's very first starlight on the cold hydrogen gas that filled all of space. To understand why this dip is so significant, we need to delve a little deeper into the delicate physics of the 21-centimeter line. Remember, the strength and even the sign of this signal, whether it appears in absorption or emission, depends on the subtle relationship between two temperatures: the kinetic temperature of the hydrogen gas itself and the temperature of the pervasive background radiation, which at this point is still the fading afterglow of the Big Bang. For millions of years after the cosmic microwave background faded, these two temperatures were coupled, both cooling in lockstep as the universe expanded. The hydrogen gas was extremely cold, but still slightly warmer than the background radiation. This meant the 21-centimeter signal should have appeared as a faint but growing absorption against the CMB. Then the first stars began to switch on. Their intense ultraviolet light, specifically the type known as Lyman alpha photons, did something remarkable. Through a complex series of interactions called the Woutheisen field effect, These photons effectively couple the hydrogen spin temperature, the temperature that determines the 21 centimeter signal, to the much hotter kinetic temperature of the gas. It's as if the first starlight flipped a cosmic switch, forcing the spin temperature to skyrocket to match the now heated gas. For a brief, cosmically significant period, this heated spin temperature would be vastly higher than the temperature of the background radiation. This is the moment of the dip. The 21 centimeter signal, now tracing this hot gas, should momentarily vanish and then reappear as a strong emission signal. It is the precise moment the first starlight announced its presence to the cosmos, not with a flash we can see, but with a specific radio signature we can try to detect. The intensity and the timing of this absorption dip are therefore a Rosetta Stone for the properties of the first stars and galaxies. A deeper, more pronounced dip would suggest that the Lyman alpha radiation from the first stars was incredibly intense, which could mean they were more numerous, more massive, or simply more efficient at producing this specific type of ultraviolet light than our models predict. Conversely, a shallower dip might indicate that the first stars were rarer or fainter. The timing of the dip's onset and its duration are equally critical. Did this signal appear when the universe was 200 million years old or 300 million? A very early dip would suggest structure formation got off to a racing start, with stars igniting shockingly quickly. A later dip would point to a more gradual, slower buildup. The shape of the dip, whether it is sharp and sudden or broad and extended, would tell us about the speed of this cosmic heating. Was it a rapid, dramatic event like turning on a spotlight, or a slow, gradual dawning like the sun rising? This is why the debate is so heated. Interpreting the dip is not straightforward because it depends on a cascade of assumptions about the unknown. The depth of the dip is exquisitely sensitive to the exact spectrum of the first starlight, which depends on the mass and temperature of those first stars. It also depends on the exact clustering of these early sources. Were they scattered evenly through space, or were they tightly packed together, creating overlapping bubbles of influence that heated the gas more efficiently? Even the nature of the dark matter itself plays a role. If dark matter is warm and suppresses small-scale structure, the first galaxies would form later and the dip would be delayed. A claimed detection by the EDGES experiment in 2018 only intensified this debate, as it reported an absorption signal twice as deep as the maximum allowed by standard astrophysical models. This startling result, if confirmed, would force a complete rewrite of our understanding of the early universe, potentially requiring new physics involving interactions between dark matter and normal matter to cool the hydrogen gas even further before the stars heated it. While the EDGES result is viewed with extreme skepticism by most of the community due to the immense difficulty of the measurement, it perfectly illustrates what is at stake. The dip is not just a signal to be found, but a complex code to be broken, one that holds the parameters of the cosmic dawn within its profile. The sheer brilliance of these ancient galaxies, shining with the fire of a trillion suns when the universe was barely out of its infancy, presents a challenge so fundamental that it has compelled cosmologists to venture beyond conventional theory and into the realm of the radical. If the standard model of cosmology, with its cold dark matter and gradual hierarchical growth, cannot easily account for such precocious giants, then perhaps our understanding of the universe's very ingredients or its rulebook for star formation requires a fundamental rewrite. This has sparked a fascinating era of theoretical creativity, with several compelling, if extraordinary, alternative explanations vying for attention. One of the most profound shifts in thinking involves re-examining the nature of dark matter itself. The prevailing model, known as cold dark matter, assumes these invisible particles move relatively slowly, allowing them to clump together efficiently and form the small-scale structures that eventually grow into galaxies. But what if dark matter isn't cold? The hypothesis of warm dark matter proposes particles that are much lighter and faster, zipping through space at a significant fraction of the speed of light. This extra motion creates a sort of gravitational pressure that suppresses the formation of structure on the smallest scales. The intriguing consequence is that while warm dark matter would delay the formation of the very first tiny galaxies, it would actually accelerate the growth of larger ones. The initial small halos that would normally form first are erased from the cosmic blueprint, funneling a larger share of the available gas into fewer, more massive halos from the very beginning. These privileged halos would then collapse with a greater abundance of raw material, potentially leading to a ferocious, explosive burst of star formation that could explain the shocking brightness Webb observes. While this idea elegantly solves the brightness problem, it faces a significant challenge from other observations, particularly the growing census of small, faint galaxies that Webb is also finding, which seem to support the cold dark matter prediction of a universe rich with small structures. Another compelling line of thought asks us to reconsider not the dark matter, but the very process of star formation in the pristine early universe. In the modern cosmos, star formation is a relatively inefficient process. Giant clouds of gas enriched with dust and heavy elements fragment into stars of all sizes, but much of the gas is blown away by stellar winds or heated too much to collapse. The early universe was a different place entirely, a vast, simple sea of pure hydrogen and helium with no dust or heavy elements to complicate things. In this environment, the physics of collapse may have been radically different, without dust to help with cooling and without the complex chemistry that leads to fragmentation. Enormous gas clouds might have collapsed in a monolithic runaway process, converting nearly 100% of their mass into stars in a single, frantic burst. This is a staggering thought. A modern stellar nursery might convert only a few percent of its gas into stars, but a primordial cloud could have achieved near total efficiency, creating a dazzlingly bright, starburst galaxy in a phenomenally short amount of time. This wouldn't require more mass than the standard model allows. It would simply mean that the mass present was used with impossible efficiency, turning entire galaxies into unimaginably productive stellar factories for a brief, glorious period. Perhaps the most dramatic alternative, however, shifts the source of the light entirely away from stars. What if the incredible brilliance Webb sees isn't from a frenzy of star formation, but from the blinding glare of supermassive black holes in their youth? This theory connects directly to the other great mystery of rapid black hole formation. Imagine that at the heart of these young galaxies lay not a modest black hole seed, but a behemoth born from the direct collapse of a gigantic gas cloud, a black hole starting its life with a mass of tens of thousands of suns. If such a monster was present and actively feeding, pulling in vast quantities of gas to form a searingly hot accretion disk, it would shine with the intensity of a quasar, outshining the collective light of every star in its host galaxy. A single such object could easily account for the anomalous brightness, making the galaxy appear mature and massive when, in fact, its brilliance is dominated by a single, unimaginably powerful engine at its core. This explanation is particularly attractive because it kills two cosmic birds with one stone, offering a natural reason for both the unexpected brightness of early galaxies and the perplexing existence of fully grown supermassive black holes in the same epoch. As the data from Webb continues to pour in, the scientific community is carefully weighing these radical options against the mounting evidence. The modified dark matter models, while elegant, are currently losing traction as Webb discovers more and more small, faint galaxies, a population that warm dark matter struggles to explain. The ultra-efficient star formation theory remains a strong contender, especially as spectroscopic analysis reveals the chemical fingerprints of these galaxies, which could indicate a singular, rapid burst of star formation with a unique pattern of elemental abundances. However, the direct collapse black hole model is gaining significant interest. Webb's spectrographs are now the ultimate arbiter, as they can distinguish between the light coming from a population of stars and the fierce, broad emission lines characteristic of an actively feeding supermassive black hole. Early results suggest a mixed picture. Some of these bright early objects show clear signatures of stellar light, while others do appear to be dominated by black hole activity. The most likely resolution to this mystery may not be a single winner, but a revelation that the early universe was far more diverse than we ever imagined, hosting multiple pathways to brilliance through a combination of these exotic and powerful processes. Every single galaxy, star, planet, and living thing we see around us is the direct legacy of that first formative era. The events of the cosmic dawn didn't just happen in the distant past. They set the fundamental rules and provided the raw materials for the entire 13.8 billion year story that followed, a story that ultimately led to us. This final mystery is perhaps the most profound of all. How the chaotic birth pangs of the universe dictated the specific, life-friendly cosmos we inhabit today, connecting the quantum fluctuations of the first instant to the planet we call home. Consider the very distribution of galaxies across the sky. That magnificent cosmic web with its brilliant clusters and long, faint filaments is not a random pattern. It is a fossil, a gigantic imprint of the initial density fluctuations that were amplified during the cosmic dawn. The specific way dark matter clumped together, guided by its own mysterious properties, created a gravitational blueprint. This blueprint determined where the first protogalaxies would form, which regions would become rich superclusters, and which would remain as vast, empty voids. The immense structures we map today, like the Laniakea supercluster that our Milky Way calls home, are simply the grown-up versions of those first, faint overdensities that coalesced in the darkness. The large-scale architecture of the entire observable universe was irrevocably locked into place during that ancient era, meaning the empty spaces we see between the stars and the galaxies are not a void, but a historical record of the universe's initial conditions. This legacy extends far beyond mere structure and into the very chemistry of existence. Before the cosmic dawn, the universe was a boringly simple place, composed only of hydrogen, helium, and a trace of lithium. It was the lives and, more importantly, the spectacular deaths of the first population, 3 stars that changed everything. Their supernova were the universe's primary alchemical factories, forging the first heavy elements in their fiery hearts and then scattering these precious ashes across the cosmos. This act of stellar recycling enriched the primordial gas with carbon, oxygen, nitrogen, silicon, and iron, the essential ingredients for everything that was to come. Every element in our bodies that is not hydrogen was created in a star, and the process began with those first massive giants. The second generation of stars that formed from this enriched gas could then form planetary systems. The dust grains that coalesced in the aftermath of those early explosions became the building blocks of rocky planets like Earth. The oxygen from those stellar explosions eventually filled our oceans and our atmosphere. The carbon became the backbone of every organic molecule. We are quite literally made of stardust, and the factory that produced that dust first opened for business during the cosmic dawn. This chemical enrichment also directly influenced the potential for life itself. A universe that remained purely hydrogen and helium could never have created planets, much less the complex chemistry required for biology. The events of the cosmic dawn set the universe on a specific chemical pathway. The specific elemental abundances produced by those first supernova, the ratio of carbon to oxygen, for instance, may have subtly influenced the chemistry of subsequent star formation and planet building. It is even possible that the explosive deaths of the very first stars seeded the early cosmos with radioactive elements like aluminum-26, which would have provided a crucial internal heat source for the first rocky planets, potentially driving plate tectonics and volcanic activity, which are thought to be key ingredients for a stable climate and the emergence of life. The habitability of our planet, and perhaps countless others, was contingent on the specific and violent astrophysical processes that occurred in the universe's first few 100 million years. Ultimately, the drive to understand the cosmic dawn is about more than just filling in a chapter of a physics textbook. It is a fundamental part of the human journey to understand our own origins and our place in the cosmos. By peering back to that first light, we are answering the most basic questions. Where did we come from? How did everything begin? Each mystery, solved from the nature of the first stars to the timing of reionization, is a piece of a larger puzzle that tells the story of how a hot, dense, simple state evolved into a cold, vast, and complex universe capable of fostering life and consciousness. It grounds our existence in a grand, physical narrative that spans billions of years, connecting the quantum to the cosmic. Every new observation from telescopes like James Webb is not just data. It is a page from our own cosmic genealogy, revealing the conditions that had to be just right for us to eventually emerge and look back wonderstruck at the dawn from which we came. And so our journey through the mysteries of the cosmic dawn draws to a close, but the story itself is far from over. We have wandered through 25 of the most profound puzzles in all of cosmology, from the enigmatic nature of the very first starlight from population 3 stars to the perplexing timeline of reionization that cleared the cosmic fog. We've grappled with the identity of the universe's first light bulbs, questioned how supermassive black holes grew so impossibly fast, and explored the invisible hand of dark matter that sculpted the cosmos from nothingness. We confronted the missing dwarf galaxies, pondered the primordial origins of magnetism, and learned to read the intricate Lyman alpha forest. The James Webb Space Telescope's shocking discovery of impossibly bright early galaxies forced us to reconsider our most fundamental models, while the hunt for the first molecule, helium hydride, revealed the humble beginnings of cosmic chemistry. We listened for the faint whisper of the 21-centimeter signal and traced the delicate filaments of the cosmic web, all while trying to measure the immense duration of the dark ages and theorize about the possibility of binary black holes dancing in the hearts of the first galaxies. We investigated the origin of the first cosmic dust, charted the universe's dramatic thermal history, and envisioned the spectacular hypernova deaths of the first stars. We studied the ancient fossils of globular clusters, connected the quantum fluctuations of inflation to the first galaxies, and watched as chaotic early rotation gave way to ordered spirals. The monumental technical challenge of detecting primordial magnetic fields and the heated debate over the precise meaning of the cosmic dawn's 21-centimeter absorption dip show us just how much there is still to learn. Each mystery is a thread in a grand tapestry, and together they form the most exciting frontier in modern astronomy. What makes this era so thrilling is that we are no longer merely theorizing, we are finally observing. We are living through a revolution in our understanding, powered by a new generation of telescopes and technologies that act as time machines, peering directly into the universe's infancy. The James Webb Space Telescope, with its unprecedented infrared vision, is rewriting the textbooks in real time. Radio arrays like the Square Kilometre Array are tuning in to the universe's faintest radio whispers. Observatories like the Vera C. Rubin Observatory are preparing to conduct a deep census of the sky, and future missions like LISA will listen for the gravitational waves from the first black hole mergers. Each new instrument brings us closer to answers than ever before, turning what were once philosophical speculations into hard, observational science. We are testing the limits of our models, and where they break, we are discovering the need for new, more brilliant physics. This isn't just a story about the distant past, it is the story of our own origin. Every element in our bodies that is not hydrogen was forged in the heart of a star that lived and died long before our sun was born. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of it was scattered across the galaxy by the explosions of those first massive stars. We are not just living in the universe, we are a product of it, a way for the cosmos to know itself. So the next time you find yourself under a clear night sky, look up. Remember that the faint light from distant stars began its journey billions of years ago, carrying with it the secrets of the cosmic dawn. Stay curious, keep wondering, and know that in seeking to understand the dawn of everything, we are ultimately discovering our own place within this grand, beautiful, and ever-unfolding story.